Okie dokie. Welcome everybody. Welcome to our YouTube class. Hopefully, oh, you can't see my screen because I've just seen it's gone up on the other screen for some reason. Let me just turn that off. That's not useful, is it? But hello, welcome everybody. Sorry, hopefully we'll be able to see my slides properly in a second once I tell it to do it on the right screen. There we go. Hopefully we can see it now. Please feel free to say hi in the chat. That looks better. But welcome everybody. Nice to have you here. This is going to be our A-level chemistry atomic structure and the periodic table web class. So it'd be nice to know if there are people who have been to sessions before. Welcome back if you have, or if you're a newbie, if this is the first time you've been to one of our YouTube sessions. So welcome if you are. Again, please feel free to say hi in the chat. It's nice to know who we've got waiting and listening and all that sort of thing. We do these web classes. We didn't do YouTube classes, we didn't do YouTube classes that regularly over the summer, but these are classes that we do regularly. So if you haven't already, please feel free to have a look back at our YouTube channel to see if there are other web classes that might be useful to you. We've done quite a few different web classes in chemistry. We also do them in biology, physics and maths as well. So yes, it may be very useful to you to go and have a look at those. If you haven't as well, the slides should be in the description, so down below. If you wanted to download today's slides, it's very useful if you want to write, for example, your notes for today, if you want to to save them for revision purposes and try and fill them in on your own for revision purposes. That's also a very good idea. But please feel free to download today's slides. They are in the description below. They are linked in the description below. But welcome. Please feel free to say hi in the chat. I will hopefully be getting you guys to answer as many questions as possible, and feel free as well to ask as many questions as you need, and we will try to answer all of them. Obviously, hopefully, mainly on atomic structure and the periodic table, but if there's anything major at the end, we may, if we have time, which is unlikely because I do like to waffle, but if we have time, we can chat about that as well. But hello, welcome. We'll get started in about 30 seconds or less than that, 15 seconds time. But yes, do feel free to say hi if you are here waiting. If this is a second or third time that you've come to one of our classes, then welcome back if this is the first time. If maybe you're a new A-level student, then welcome to A-levels. I'm sure that the first couple of weeks of September have been a challenge, but hopefully this can act as a bit of a revision for you, and we can get we can improve your understanding of atomic structure and the periodic table. So tiny bit about me before we get started. Oh, hello, there we go. My name's Alyssa. I have been teaching with Snap Provise now for 3 years. I am the lead chemistry teacher here. I have a PGCE in science, specifically chemistry being my favourite. And I've been teaching and tutoring A-levels and Key Stage 3 all the way up to A-level sciences for over 7 years now. So love it. It is my favourite. Science is, I think, amazing. Our objectives for today are to look at or remind ourselves of the GCSE knowledge that we hopefully know of atomic structure and the periodic table. And we're going to look at understanding atomic structure in terms of isotopes and ions, and understand and be able to calculate relative atomic and or isotopic masses. So we'll look at what those mean in a bit. We're not going to look at the history of the atomic structure. So things like the Bohr model, Rutherford's model, Thomson plum pudding model, etc., which is stuff that you do need to know, but it's not something that we're going to cover together. Oh, good question. Is this for A-level or bridging the two? This is definitely A-level content. This is all A-level content. It just happens that a lot of the stuff that you do at the beginning of year 12 in A-level chemistry is your GCSE content. So there isn't a lot of overlap, but there are still some key details that do need to be understood. But great question. Okay, so just have a quick look at the specification points for the content that we're going to be looking at. So this is the specification points for AQA. So if you're an AQA student, you'll find this in your specification. This is what we're going to be covering. For OCR, these are the specification points, but if you're an OCR student, this is what we're going to be covering for you. And this is the specification points for Edexcel that we're going to be covering. Notice all the specifications are very different. If you haven't already, I would highly, highly recommend becoming very well acquainted with your specification, because some are more useful than others, but they are the things that we have to know, basically. That's what we need to know for our exams. Okay, so let's have a look then at what we already know. So hopefully this is GCSE content, which we can just remind ourselves of. So we've got Bohr's model of the atom on the left here. So this is where we've got our central bit. So this is all of our content. That's a very good question as well. So the content that we cover is for everybody. There's a huge amount of overlap between all of the exam boards. If there's anything that is not in a specific exam board or is only in a specific exam board, then I will tell you. Otherwise, it's the same across exam boards, if that makes sense. So we do cover all three of the main exam boards and all their content. So it is relevant for anybody, basically. What does anybody know, and can anyone name or recognize any of the subatomic particles or any of the parts of an atom? What are these things here that we've got going on? What are these bits? Does anybody know? Can we name them? Can we recognize what they are? Lovely. We've got some neutrons. We've got protons. Very good. Very nice. Well done. Welcome, everybody, by the way. Welcome, welcome. Hi, hi. Good. We've got electrons as well. Anything else? What other aspects of an atom have I highlighted? If at any point you can't read my handwriting as well, please feel free to say. Anybody know? Good. The shells, or specifically the one I've pointed to, that's nice, is the valence shell, but electron shells, I'm going to be a bit more general. And then the nucleus. Really nice, guys. Well done. Fantastic. Lovely. Cool. So those bits, hopefully we're nice and confident with what those bits, these parts of the atom are. On the right-hand side here is how we would usually represent an element. So X is our element. Can you tell me what A and Z are? When we write the chemical symbol for an element, we represent that element using two numbers. What are those numbers? Which is A and which is Z? Do you know which one's which and what they represent? What's A and what's Z? So we can represent atoms using, oh, you've been very specific. That's nice. What I want, rather than you being specific, can you tell me what that number is? Notice that actually in my structure of an atom, it's not a model of an actual atom, because we've got a very odd discrepancy between the number of protons and the number of electrons. Yes, that's what I was saying, Kai. Well, it doesn't matter actually if you have an imbalance of protons and neutrons, because lots of our atoms do have an imbalance of protons and neutrons. The thing that I'm struggling with here is the imbalance of protons and electrons. So in this model that we've got going on here, it's just obviously not a model of an actual atom, because we've got such a discrepancy between the number of protons and the number of electrons. I mean, it could just be a highly charged ion, but it's not an atom. Excuse me. But in general, A is our atomic number. So A is the atomic number, and Z is our mass number. I've got that the wrong way around. My notes must be wrong, because Z is the charged one, isn't it? Apologies. Z is the charged number. So we've got our mass number and our atomic number. Not always given that way around in terms of top and bottom. So just be aware. You just need to make sure you know which is the bigger number, and the bigger number is the mass number. The smaller number is the atomic number. This bottom box, what's our relative? I know I've said actual, but I want to know relative. I've just realized I'm still in red. I'm going to come out of red in a second. What's our relative mass of protons? What's the relative mass of neutrons? And what's the relative mass of electrons? Anyone know? What's the relative mass of protons, neutrons, and electrons? Oh, I've got a flag flying on me. Anyone know? And I have specifically said relative because I don't want the exact mass. We don't, in A-level chemistry, we don't actually care about the actual mass of protons, neutrons, and electrons. If you're a physicist, you will need to be aware of and be able to use the actual masses, but we don't in chemistry, which is nice. Nice, good. Okay, so interestingly, at GCSE, so we have our mass of proton is 1, the mass of the neutron is 1, and the mass of electron is negligible. Oh, couldn't spell that then. In GCSE, they are much more interested in you giving an exact mass. So you can say 1/1836, or anything that rounds to that. So 1/2000 or 1/1800. So you can know either, but at A-level, they're not actually as worried. So you can say negligible, or at least we can consider it to be negligible, so that we can get we can do a lot more of our maths, as it were, and use a lot of our what's my brain's not using the right word. We can apply a lot of our content and a lot of our theory if we assume that the mass of electron is negligible. Nice, lovely, well done. Okay, let's keep going. I'm going to just change my pen color because I don't like writing in red. Okay, so this is a web class on atomic structure and the periodic table. So let's talk a little bit about the periodic table. What do you know about the periodic table? What do you know about the columns? Columns equals what? And what are the rows? Rows equals what? Are there any areas of the periodic table that you can talk to me about, that you know the names of? Can you put in any numbers anywhere? What do we know already? Lovely, that's a really nice place to start. What's the names of these as well? The name of a column. So I'm describing it as a column, but then we have a name for the columns, and we also have a name for the rows. What are they? So the columns represent something which is the number of electrons in the outer shell. Very nice. Yes, lovely, good. So the columns represent the groups of the periodic table. And the group number is the number of electrons in the outer shell. Oops, I didn't finish that. Shell. Very nice, well done. And then the rows are the periods, very nice. And the periods in a periodic table. So the period comes from, the name periodic table comes from the fact that there are periods. And a period is a repeating pattern. And in this case, it's a repeating pattern of chemical reactions. That's why our elements are in the groups, because every row, every period is a repeating pattern of how these elements react. So the rows represent the periods, which is the number of shells which contain electrons. And hopefully everyone's happy with me calling an electron an E-, just being lazy. Okay, lovely. Group 1 and group 2 have a valence electron in an s orbital. Good. So we've got different sections of the periodic table. At GCSE, we haven't yet covered valent orbitals, but 1, 2, 3, 4, 5, 6, 7, and 8, we do give, or 0 actually, we do give them numbers though. We do give our groups, and lovely, we also, something we do also need to do, or we do at GCSE, is we note that the middle section is called the transition metals. Very nice. You have given me some other information which is extra, which is great, but we're just going to do that to begin with. Lovely. Okay. So this we all need to know, and we do still need to know at A level. So this is stuff we did at GCSE, but we also need to know for A level. So now let's have a build on it. Is there any specific note on the color of each atom? So you need to know colors of some at A level. We're not going to cover it today, but just so that you're aware, you do need to know colors of some transition metal compounds. You also need to know colors in terms of flame test colors for various metals. What are the colors? I can't think what other colors you need to know. There are various color related stuff you need to know about various different atoms within the periodic table. Is this applicable for all boards? Yes, it is. Yep. If there's anything that's a discrepancy between the boards, so something that's not present in an exam board or is in an exam board, I will point it out. But especially at the beginning of A-level chemistry, it is identical across the boards. Okay, let's look at atomic structure then, and add on to this knowledge that we already have in terms of our A-level content. So we hopefully already know that the atomic number is unique for each element, as in if you pick, so it's about 50 minutes or so, we should be finished in about 50 minutes. But hello, welcome everybody. It's lovely to see we've got lots of people here. That's fantastic. So if you pick up an atom and you count the number of protons, you work out what its atomic number is, then you know what type of atom that is. You know what element that atom is. If you change the number of protons, you change that element. Hopefully we already know that, but that's it. I think a key point when thinking about our atoms and isotopes and elements and things like that. So building on our GCSE content, when we determine the mass of an element, what do? What value do we use for the mass of an element? Does anyone know how do we work out the mass of an element? If you've got a periodic table in front of you and you're trying to find the atomic mass, what do we use? And what does that number represent? Oh, that's an interesting question. So that was a bad question by me. So if I had, can't think of an example. Let's use aluminium, for example. The bigger number, which here is on the bottom, is my mass number. What does that tell me? Is that number representing? There's a sound. Is there a sound problem? Can you guys not hear me properly? It should be fine. My oh gosh, something's gone funny. Sorry, my screen's just gone blank for no reason, just as you said that. So there must be something going wrong. Not quite sure what's happened. I'm just going to see. I don't really know what's happened. I think it's my laptop has just decided to restart itself. Wow, that was interesting. Oh, sorry guys, I don't know if anyone can still hear me or anything, but my laptop has just decided to restart itself, I think, because the screen went black and then I had to log myself in again. And now it's now not letting me do anything, it's now frozen. I think we've got a bit of a technical hitch. Work out if you guys can still see me. Or hear me. I'm just going to close this in case that makes a difference. I'm back. Am I back? Apologies for that, guys. Right, I'm sorry. Haven't got a clue. I think my laptop decided it needed to restart itself. For no apparent reason. I definitely didn't tell it to. We were in the middle of a class. So let's just try this. Let me know if you can see me and hear me and everything, guys. While I just make sure I can read your chat again, because that's just sorted itself out. Sorry, guys. That's technology for you. You can see everyone else is right. Okay, it was just that. Okay, we're back. I don't know what went on. Apologies for that, guys. We love technology, don't we? And actually, technology is normally very nice to me, apart from on occasion when it decides not to be. Okay, everyone, cool. We're all sorted. Lovely. Okay, I think we're back, and I think it's all happy, and it's decided. Don't know what it was doing. I think my laptop was just having a funny 5. Okay, lovely. Good. Okay, right. Where did we get to? We got to mass of an element being number of protons plus the number of neutrons. So let's just pop that in. So when we're working out our mass of stuff, this is why we decide to say that our mass of electrons is negligible, because then we don't have to include it in any of our calculations or anything. So when we're working out the mass of an element or mass of an atom, we work out the number of protons plus the number of neutrons. So why do we need to be specific when we talk about whether we're doing a mass of an element versus the mass of an isotope or of that element, or a mass of an atom, etc.? What is an isotope? Why is that important for us to specify, do we think? Does anyone know? What is an isotope? Lovely, that's a really nice definition. Fantastic. It is good. So to the I like that that phrase there. It's a varying number of neutrons. So isotopes are atoms of each of a specific element. So an isotope is an atom of an element. So it has a specific proton number, but it may have different neutron numbers, and therefore the mass number will be different. Very good. So an atom of an element with the same number of protons, because it is that element. So if it is that element, it cannot have anything other than what we would call the normal number of protons, but differing numbers, or a differing number of neutrons. So for example, carbon-13 and carbon-12 are isotopes of the same element because they have different numbers of neutrons but the same number of protons. And they have the same atomic number, which is what tells us the number of protons, but a different mass number, which is what tells us the number of protons plus neutrons. Awesome. Okay, hopefully everyone is confident with that. If you're not, drop me a question in the chat. Otherwise, we will keep going. So we can look at carbon as an example. Carbon isotopes are really useful to learn about because carbon is so useful. We are what we call carbon-based life forms. Life on Earth is carbon-based. A huge amount of everything you're looking at, that you're made of, that you touch, etc., is carbon-based. So carbon is incredibly important to us. Carbon-12 is what we are normally encountering, what we're used to encountering. Carbon-12 has got 6 protons. It has to have 6 protons because it's carbon. But if it's carbon-12, how many neutrons does it have? How many neutrons does carbon-12 have? Can you work it out? How many neutrons? So we've got carbon. It has got how many neutrons, how many protons? We've got 6 protons, so how many neutrons must it have? Good, lovely. And I like the fact that you've included the equation in there, because it's got a mass number of 6. That's why we call it carbon-12. That's telling us the mass number. Therefore, 6 protons because it's carbon, and therefore must have 6 neutrons, 6 plus 6 being 12. Carbon-13, you knew what I was going to ask. If it's got carbon-13, that means it's got the same number of protons. It's still got 6 protons, but it's got 13 mass number of 13, which must mean it's got 7 neutrons. Very nice. And then carbon-14 has got 6 protons because it's carbon. It's got a mass number of 14, which therefore means there must be 8 neutrons. Very nice. Okay, fantastic. All of these are very useful. So carbon-12 is what makes up a lot of the carbon atoms in the world. 98.9% of carbon atoms are carbon-12. That's what makes up life. But carbon-13 is very useful. We use it for what we call NMR spectroscopy, which is a analytical technique you do learn about at A level. And then carbon-14 is very useful for things like radiocarbon dating and stuff like that. So carbon is a very useful example to know. You don't have to know it off by heart, but it is useful to know it off by heart. Let's have a look at atoms versus ions as well. This is a useful bit of content, which again, you do at GCSE, but we need to make sure we're sure about at A level. So an ion is a charged atom or molecule or group of atoms. The charge of an atom depends on the balance of charge between the protons and electrons. As we hopefully can see / already know, when you've got protons, protons are positively charged, electrons are negatively charged. And in an atom has got an equal number of protons and electrons, which is why the charge is neutral. However, when we have a charged particle and we have an imbalance, we end up with a charge. So how do you guys remember which one's which? Cation versus anion. Have you been taught a way to remember which one's which yet? Maybe at GCSE? It is the gain or loss of electrons leading to the imbalance of charges. Very nice. What's the difference between a cation and an anion? How do you remember which one's which? Yeah, that's what I do as well. Total recall, that's what I do. So I've always said a cation is positive or positive. So a cation is positive because it pairs, or positive. So cations are positive or positively charged. And anions are negatively charged. Okay, I think it's worth or it is worth remembering the ions. Make sure you are sure about what the ion is. So cation is positively charged and anion is negatively charged. And then use those to work out the differences between anodes and cathodes when you get on to doing that sort of thing. Okay, so then we also said we've got a neutral atom. So atoms, when we talk about atoms, we're usually talking about a neutral atom. We're just lazy, so we don't always state that it's neutral. So neutral atoms, where the charges are balanced, we have the same number of protons and electrons. How do we recognize, or what do we use to represent ions? What do you need to add to a diagram to represent an ion? What do I need to add to my pictures here of dot and cross diagrams, sort of, to show that they are charged? Superscript numbers, good, very nice. And what else? Brackets, very nice, good. Brackets and then the positive or negative. And if there's a number of them, then the number of them. Very nice, well done, perfect. So this left-hand one, we've got 5 protons, 4 electrons. So the total charge is going to be +1, but because we're lazy chemists, lazy scientists, we don't put the 1 in because we can't be bothered. And absolutely right, when we're drawing similarly, when we're drawing our negatively charged ion, we've got 5 protons and 1, 2, 3, 4, 5, 6, just checking, 6 electrons. Then we're going to have 1 negative charge. Again, we're lazy, so we don't put our number 1 in, we just put the negative. Fantastic, very nice. Okay, good. So really good idea when we're going through content, or when you're going through content mainly, for you to check how confident you're feeling. Now, hopefully everyone's feeling nice and positive about that, but how do you feel about recognizing ions, recognizing whether they're cations or anions, and determining numbers of protons, neutrons, and electrons? How do you feel? How confident do you feel about all of that? Just either give me a smiley face or a 1. It's the way of you guys recognizing how confident you are, but you can also tell me as well. A 2 or a medium face if yeah, it's all right, I think, maybe. Or 3 if, oh my gosh, no, maybe this is the first time you ever come across it or you hate it. How are you feeling? Let me know, how are you feeling? Nice. Awesome. Even better, fantastic. Lovely, well, that's good. Good. Okay, fantastic. Let's have a go at an exam question then. So this is a genuine past paper exam question. So it says, tin mining was common practice on Dartmoor in pre-Roman times. Most of the tin extracted was mixed with copper to produce bronze. Lovely. The table below shows the subatomic particles of an isotope of tin. Complete the table. So if you can do P, N, and E, can you tell me how many protons, neutrons, and electrons I need to write in here? You may need a periodic table. If you use P, N, and E, can you tell me how many protons, neutrons, and electrons do I need to write into these boxes? Bear in mind, I have to get all 3 right to get the mark. It's only worth 1 mark at A level. What are we thinking? Maybe you might need a calculator, depending on your mental math skills. Anyone got any thoughts? You may need a periodic table. You may also need a calculator, depending on your mental math skills. How many protons, neutrons, and electrons would I expect to see in this isotope? I lost my periodic table. Uh-oh. If you can, this is a note for everybody. It's a really good idea to get the data sheet that belongs to your exam board. You can just go on your exam board website, or even just Google data sheet OCR or datasheet AQA A-level chemistry, and it will give you, you'll be able to download the datasheet, and maybe you could laminate it and keep it with you, or B, just take it into your lessons with you, because you'll get used to exactly where to find information. You'll get used to exactly how the periodic table is laid out for you and how a lot of other information is given out to you, which is different per exam board. So it's really useful, I think, to have your exam board's data sheet so that you know exactly what information is going to be given to you in an exam. Lovely. That's a good one. Well done, you guys. Fantastic. Well done. Awesome. So protons, it's a tin atom. All tin atoms, or all tin isotopes, all tin elements will have 50 protons. So that is decided because we've got tin. Because it's an isotope of tin, it's not an ion, so we're assuming it's an atom. If it's an atom, there must be neutrally charged, which means there must be the same number of protons as electrons, same number of positives as negatives, so that's good. And the number of neutrons must be, as you guys have said, 68, because 118 is the mass number of tin, and the mass number is protons plus neutrons. So we must work out what 50 plus what makes 118, and it's 68. Very nice. Part 2 says, in terms of subatomic particles, how would atoms of 120 tin differ from atoms of tin 118? In terms of subatomic particles, so you need to write your answer in terms of subatomic particles, otherwise you won't get to the mark. How would atoms of tin 120 differ from atoms of tin 118? Perfect. Easy peasy, you would get the marks. So it doesn't matter which way around you say it, but exactly right. Tin 120 would have 2 more. Or you could give the total number. It would have, oh, can't count, not 80, 70 neutrons than tin 118. Really nice. Fantastic, guys. Okay, so hopefully everyone's confident with that. Let's have a look at relative mass. Now, this is, again, something that you do at GCSE level. We do the almost identical thing at A level, but the trouble is the application of the knowledge and the application of the theory that goes with it is harder. So the exam questions we've got here are harder. Okay, so let's just have a look at the basics together, which hopefully, again, we all know. So relative atomic mass, which is usually written as AR, or sometimes you may see, like in olden papers, it's written as RAM, relative atomic mass, but we should really be using AR, big A, little r. That's our relative atomic mass. So all the masses on the periodic table are relative to carbon-12. You'll notice, specifically if you are in, let me just check which ones. All of them, I think. I'm just double checking. Yes. So all 3 exam boards need to be able to give a definition of relative atomic mass as relative to 1/12 the mass of carbon-12. So for example, hydrogen, which has a relative atomic mass of 1, has a relative atomic mass of 1 because it is 1 relative to 1/12 the mass of carbon-12. So the masses on the periodic table, they are given as weighted masses. What are they weighted using? Why do they need to be weighted? Do we know what's taken into account when we do our weighting, as it were? So, for example, you might see that hydrogen is often written as 1.001. It has a mass of 1.001. Where's the 0.1 come from? Or, for example, I can't think of another example. Chlorine is 35.5. Why is it 0.5? Why have we got an imperfect number? Why is it not? Why is there a decimal number in there? So they are relative to carbon-12. However, that doesn't explain why there are decimal values. Why, for example, might aluminium's relative atomic mass be 26.98, or carbon, I think, is 12.018 or something like that. Good. Yes. Fantastic. Exactly right. So it's because they are weighted against, it's an average mass of all atoms that exist. Really nice. It's an average of all of the isotopic masses, the masses of all the different isotopes that exist of an element. Very nice. Well done. So the masses on the periodic table are a weighted average of the relative isotopic masses, the masses of all the different isotopes in the world based on their percentage abundance. Actually, let's put of an element in there. Oh no, sorry, pressed the wrong button. Go back. Of an element. How do we calculate it? How do we calculate relative atomic mass? Is there a basic equation that we know? How do we calculate it? What's the equation that we use to work out relative atomic masses? If it needs to be a weighted average of all of the relative isotopic masses of an element, how do we do that? Usually. And it's the same as GCSE as it is at A level. Anyone know? Fair enough. And I think that's probably the same for a lot of students. So you may think, well, actually, if I'm given numbers, I can work it out. But what we need to do, or the general equation, is the sum of, so that's sigma, the funny, looks like a bit like an M on its side, or a big capital E, sigma, so the sum of the mass of an isotope times the percentage abundance of that isotope. And then we divide all of that. That's it. There we go. Really nice. By 100. Fantastic. Yeah, perfect. So it's the sum of the mass of an isotope times by the percentage abundance of that isotope divided by 100. And we do that. We add up all of the values of all the different isotopes that exist and then divide by 100. Let's do an example of that. Hopefully you guys are going to find this easy. So how do we work out, or how do we get to a relative atomic mass of 12.025? What calculation do we need to do? So feel free to just do it yourself and just check that you can get that number. What do we need to do? So we should do, well, it's a sum of all of them. So I'm going to add up the mass of my isotope, so carbon-12. So the mass of that carbon-12 is 12 times by the percentage abundance, which is 98.9. I'm going to add that to my carbon-13, which has a mass of 13, but there's only 1.1% of it. And I'm going to add that to my mass isotopes with a mass of isotopes with a mass of 14, of which there is actually less than 0.1%, but we're going to say 0.1%. And we divide all of that by 100. And what we're doing by doing that is we're working out the average mass of carbon atoms. The average mass of carbon atoms is 12.025. Now, key exam tip is, in an exam, especially at A level, if you're given a relative atomic mass to work out using relative isotopic masses, the chances are the value that you work it out to be will be ever so slightly different to the value on a periodic table. Because of course, hopefully we recognize that our relative atomic masses are given on the periodic table. So if a question in an exam is asking you for a relative atomic mass of something, technically, you could just give it the value on the periodic table. However, our A-level exams will say something along the lines of using this data, or they will give you a load of information and then say calculate, which means we have to use the data given. We have to use the information that they've given to us to come up with an answer. And the chances are that that answer will be ever so slightly different to the one on the periodic table. So what we can do is we can check that the value we come up with is near to the value on the periodic table. It may not be identical, because otherwise what's the point in them asking us to do a calculation? So it might not be identical, but it should be near to. So you'll notice that this is 12.025, whereas in your periodic table, it is likely to just be 12.0. So we're not worried, basically, if the value we come out with is not the same as the periodic table, but it is make sure that it's near. If I'd worked out the average mass of carbon atoms to be 6 or near to 6, I've probably made a mistake because that's nowhere near the number on the periodic table. So it's a good check, but just don't worry if it's not identical. Okay, let's keep going. So that's relative atomic mass, the average mass of an element, of an atom of each, of the average mass of all isotopes of an element that exist. But we also need to be able to calculate the relative molecular mass. So relative molecular mass is the sum of the relative atomic masses of atoms in a molecule. So it's the sum of the relative atomic masses of all atoms in a molecule. And hopefully, again, this is GCSE content, but hopefully we're happy with what a molecule is. A molecule is two or more atoms that are covalently bonded together. Is what we describe as a molecule. They are discrete, specific sized objects, tiny, tiny objects. So if we're going to work out then the relative molecular mass of this thing, bear in mind we've been given our relative atomic masses. What is it? Ah, very nice. What is it and how do we calculate it? That's really nicely done. Well, we know, or we can see, we've got one carbon atom and we've got two oxygens. So we do our value, relative atomic mass of carbon, which is 12.011, plus, or which has been given as 12.011, plus 2 lots of the relative atomic mass of oxygen, which is 15.999, or is given as 15.999. So we need to use these values because they're the ones that have been given. And we're going to come out with a relative atomic mass of 44.009, which is our relative molecular mass, the relative molecular mass of carbon dioxide. It is approximately 44. Really, really good. Okay, we've got 10 minutes, just over 10 minutes to have a go at some exam questions. So let me know if you're feeling not so confident about that. But I do want to have a go at doing these exam questions because these are the sneaky, horrible kind of exam questions that they like to ask at A level. So if anyone's not feeling confident, then let me know. If you're feeling super confident, give me a smiley face or a 1, or if you're thinking it's okay, then give me a 2 or a oop. And if you're super confused, feel free to give me a 3. Oh, that's a very good question that I didn't mention, isn't it? How many significant figures should we give answers to? It should tell you in the question, especially with these types of questions. They are very good actually at telling you how many significant figures they want it to. But as a general rule of thumb, you should give it to, you cannot give it to any more significant figures than they do. So here, they have, oops, meant to highlight it all. Here they've given it to 5 significant figures. So because the data that I've been given in the question, it's not actually a question, is it? But in our question is 5 significant figures. I should give my answer to 5 significant figures. I can't give it to 6 or 7 or 8 because I don't have that data. So you can only give it to the number of significant figures, the minimum number of significant figures given in the question. If you're unsure, what I would do is do your full calculation to as many significant figures as you think is appropriate. And then if you think maybe you should round it, then give the other answer rounded. So you'd give your full answer and then you would give a rounded answer. So that way you're showing your examiner that you've made no mistakes on the calculation. What you have done, however, is rounded it. But in this case, because they've very definitely given us to 5 significant figures, we should give it to 5. Okay, let's do these exam questions then. I'm going to give you a couple of a minute or so to have a go. Part B, we should be able to do relatively quickly, so let's just do that together now. What is the structure of a 1+ ion of the carbon-13 isotope? A, B, C, or D? Take a second to think about it. What's the structure of a 1+ ion of the carbon-13 isotope? Just have a think, and then if you think you've got an answer, then put it in the chat. If you're not sure, have a go. It doesn't matter if you get it wrong. This isn't an exam, but have a go. What do you think? Anyone feeling confident? I think a good place to start is to work out how many protons you're expecting it to be, because it's carbon. Carbon has to have 6 protons, so it cannot be D. So that we've already gotten rid of 1. It's a 1+ ion, so if it's got 6 protons, but it's a 1+ ion, we must have more protons than electrons. So it can't be A, because A's got 5 electrons, and it can't be, sorry, wrong one. Can't be B, apologies, because it's got the same number of protons as electrons. So we've therefore eliminated another answer. So we've got to have more protons than electrons. And then it's how many more? Well, just 1 more. So it's got to have 5 electrons. Well, it could be either A or C then. So then it's on to how many neutrons is it? Well, it's a carbon-13 isotope, which means I've got 7 neutrons. So absolutely correct. Well done if you said C. Awesome. Very good. CI says, state what is meant by the term relative atomic mass. So just because we're slightly low on time, I'm going to write it out, but make sure that you are thinking, what would you write for this? What is meant by the term relative atomic mass? So you need to say that it is the weighted average of all isotopes of an element relative to 1/12 the mass of carbon-12. Now, unfortunately, you don't have to use the term weighted, but you do need to talk about the fact that it is an average mass of all isotopes of an element according to their percentage abundance. So you could, yeah, so lovely, Mohammed, that looks great. Because you've mentioned their percentage abundances, that's the same as saying weighted, and that's fine, that's lovely. But you have to have something in there about the weightedness, and then it has to be relative. Oh, I can't spell apparently. Relative to 1/12 the mass of carbon-12 for the second mark. Okay, so you have to say both. Awesome. Okay, part 2, C2. And this is where our questions get a little bit trickier. Hopefully we'll have a chance to do the next one as well, but here we go. Question 2 says, a 5-gram sample of lithium containing the 2 isotopes, lithium-6 and lithium-7, was found to contain 0.46 grams of the isotope lithium-6. So we've got 5 grams of lithium, 0.46 of it is lithium-6. Calculate the relative atomic mass of lithium for this sample. Give your answer to an appropriate number of significant figures. So this is slightly different to what we're used to. Feel free to go ahead and have a go at calculating a relative atomic mass. But anybody got any ideas how we're going to do this? Is there a step that we could do first? Or because we've not got percentage abundances here. We've not been given a percentage abundances. So we're going to need to tackle this question slightly differently. What are we going to do? How can we do this? Lovely. Great, Kai. That is exactly what I would do. With our percentages, percent is a fraction. It's something out of 100. So we can either work out what those percentages are. Fairly exactly, you can do that. You can work out what the percentages are that we've got here. Or you can choose to just use, instead of it as a percentage, we use it as a fraction of what we've got. Instead of it being a percentage, which is the same thing, it's just times 100 to get it as a percentage, but we can just do it as a fraction. Yeah, good. Okay, and it's the same formula again. Really nice. Go on then, have a go, plug your numbers into a calculator, see if you can come up with an answer. So I'm going to do lithium 6 first. So lithium 6 is 0.46 grams. Oops, not 0.66, it's 0.46 grams out of the 5 grams. So 0.46 out of 5, that's effectively my percentage, but it's not given as a percentage, it's just given as a fraction. And has a relative isotopic mass, it has a mass of 6.15, added to, what have we got? The rest of it, so I'm going to need a little bit of mass here. The rest of it is 5 minus 0.46. Again, divided by 5 grams, because that's my fraction, or my equivalent of a percentage, times by 7.016. And that should give me, plug those numbers in, 0.46 over 5 times 6.015. Add that to 5, the difference between the two, over 5 times by 7.016 should give me if I write out the full number first, 6.923908. And it says, okay, we're not going to have a time to go through the final question. Apologies, guys. But just to come back to the question we said about significant figures, calculate the relative atomic mass of lithium for this sample. Give your answer to an appropriate number of significant figures. So we need to determine what an appropriate number is. So what I'm going to do is look back at the question. Here, I've got 4 significant figures. Here, I've only got 3 significant figures. And then down here, I've got 4 and 4. So because I've been given 3 as my smallest number of significant figures, I have to give my answer to 3 significant figures. It's a really sneaky, and they're really mean because there's 3 lots of 4 significant figures in the question, but there is 1 lot of 3 significant figures. So my answer has to be 3. And I'm totally understand why people get tripped up by this question, because they will do. 100% they will get tripped up by this question, because you've noticed quite correctly that there are 3 lots of 4 significant figures in this question. But we have to be very clear, and this is why they've asked this question, that there is 1 which is only 3, which means I have to give my answer to 3 significant figures. I can't give it any more. Okay. And 100% this is A level, but if you're finding this nice and simple, amazing, because this is genuine past paper questions. Okay, we've only got 1 minute left, so unfortunately we're not going to be able to have a go at this, but please do have a go. I'll tell you now what the answer is, and then hopefully you guys can have a go in your own time and work out what the correct answer is. But it says calculate the percentage abundance of boron 10 in this naturally occurring sample of boron, and the percentage abundance is 20% of boron 10. Okay, so I'm going to skip ahead just so we can finish. We've covered our GCSE content of atomic structure in the periodic table. We've looked at understanding atomic structure in terms of isotopes and ions. and we've looked at calculating relative atomic and isotopic masses. Does anyone have any questions? We've got a couple of questions I'm going to answer now. So this video is video 1, it is, of our year 12 content. So this is our, what we would class maybe our most basic A-level content web class. So we have lots and lots. If there's something you're interested in, please go and have a look at snapprovise.co.uk and have a go at have a look at what we've got to offer. We've got loads on there, including web classes and stuff that you can sign up for. We will do web classes we do web classes in biology, physics, chemistry and maths. There will be YouTube classes every Sunday. It's not 100% every Sunday, but it's almost every Sunday for now, between now and the rest of the year. So please keep an eye out for when we've got web classes coming up. We did have GCSE. I know someone asked this earlier. We did have GCSE, but it's not, we're not doing it at the moment. It may come back, it may not. Just keep your eyes peeled. It may come back, it may not. There's free content that you can go and download on our website. So please go and investigate that and get downloading. And again, like I said at the beginning, go back through our YouTube channel and rewatch some of our web classes, because we've got loads on there that you can go back and watch, and that's all for free, obviously, because it's on YouTube. The schedule we've just popped in the chat so you can have a look at what we've got upcoming. And yeah, awesome. So organic chemistry, I know, is very hard. It is. There is a lot of content out there, but again, please feel free to go on to SnapProvise. We offer web classes as part of a subscription service, so you can go on and have a go. And then we do, it's 5 web classes. 1, 2, 3, no, I can't count. 4 web classes per subject per week that you can have a look at, plus a load of previous web classes as well. So feel free to go on there and have a look. And lovely, and I hope to see you guys soon at a future web class. Thank you very much. Well done for being so awesome. Have a lovely evening/day. Yes, awesome. Thanks, guys. Well done. I will see you soon.